Nature is nonlinear. Nature is mechanics. Nature is composite. Nature is structured. In short, nature is the dance of nonlinear mechanics of composite structures. प्रकृति गैर रैखिक है, प्रकृति यांत्रिकी है, प्रकृति समग्र है, प्रकृति संरचित है. संक्षेप में प्रकृति समग्र संरचनाओं के गैर रैखिक यांत्रिकी का नृत्य है. भूमिमंगलम भूमिमंगलम उदकमंगलम उदकमंगलम अग्निमंगलम अग्निमंगलम वायुमंगलम वायुमंगलम गगनमंगलम गगनमंगलम सूर्यमंगलम सूर्यमंगलम चंद्रमंगलम चंद्रमंगलम जगतमंगलम जगतमंगलम जीवमंगलम जीवमंगलम देहमंगलम देहमंगलम मनोमंगलम मनोमंगलम आत्ममंगलम आत्ममंगलम भूमिमंगलम उदकमंगलम अग्निमंगलम वायुमंगलम गगनमंगलम सूर्यमंगलम चंद्रमंगलम जगतमंगलम जीवमंगलम देहमंगलम मनोमंगलम आत्ममंगलम सर्वमंगलम भवतु 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 सर्वमंगलम भवतु 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 सर्वमंगलम भवतु भवतु भवतु. Om.
Good morning, everybody. Can you see my slide?
Yes, sir.
Okay.
Good morning, sir.
Good morning. Thank you.
Yes.
So let's go ahead with the third class for the nonlinear mechanics of composite structures, AE352. Today's class, we will continue with the big overview that we had in the previous class, where we looked at what we perceive more of a leadership role in doing a 300 level course, which is typically a doctoral level course. What is the topic that we are about to address throughout this set of lectures? Maybe you would have about 25-30 lectures. So through these lectures of about 50 hours, what is it that we are trying to explore? We need to understand the bigger picture to start with, so that way everything will be put into perspective when we look at the details. So that was the whole idea of presenting that bigger picture. So we will continue doing that to probably a few minutes in the beginning of today's class, and then we will get on to some kind of a course information. Prior to that, we'll also look at the modeling overview. Because the whole idea of nonlinear mechanics of composite structures is there's something which is observed in reality and you want to model that. So what is the approach that we are going to take towards modeling? What is modeling in general, and what is the need for having new models, which is what we are going to accomplish through this course for the composite structures. So before we get on to the equations and the way to solve those problems, we need to understand from a linguistic perspective what all of these are motivated by. We already saw the motivation for composites in the first class, and we also looked at certain aspects of nonlinearity in the previous class. So now we look at the other aspects of modeling, the way it is traditionally done, and the way we are going to do it, and why we need to have a divergence or difference from what it is in the traditional sense, especially the linear models, and also certain other non-linear models which exist in the literature and also as part of well-known commercial software like Abacus, ANSYS, Nastran, etc. So we have a way of doing it which is different. So why do we need to take that new approach? What is the gap that is there between the existing nonlinear models that are there in all of these commercial software? Especially Abacus has excellent nonlinear capabilities, but there is something that we can do even more. And what is it that we can do even more is what we will look at when we look at the need for the new models in today's class. So as I said before, we do all of that, we will first get on to summarizing what we had explored in the previous class in terms of the overall course title understanding. So we had said that nonlinear basically refers to the ability to perceive reality within the model. And when we say within, we also refer to the fact that it is so we say even within or even amidst. So the whole idea is that everybody perceives the model, but how do we perceive the model? For which we should have developed the model in a particular way. Then only we can perceive the reality within the model. If the model is done in an oversimplified way, for example, then obviously it is far off from reality, and therefore there's hardly a tinge of reality within the model. So there itself we are looking at the need to develop a model in a particular fashion. So that is the whole idea of that. So that's why I say even amidst. So underlining that fact that it is even. So everybody sees the model, but we see the reality in the model because of the way we have developed the model. So we'll get into a little bit more about that as we progress in today's class. Then the second aspect is as far as the mechanics is concerned, where we looked at what everybody else sees as motion. We are able to see a stationary principle within that, just like what Mr. Lagrange did, or Mr. Hamilton did, or which Mr. Jacobian did, or as we shall see more relevant to our course, what Professor Berdychevsky saw. I'll introduce him to you later in today's class, but these are all gentlemen who have come up with various stationary principles using which we can analyze motion, and statics as a special case of that. So even within that motion, we are able to perceive those stationary principles. And when we talk about motion as dynamics, statics as a special case, just like though we call it nonlinear, which means it is not linear, but still we deal with linear as a special case of that. So this is how we will be progressing in a superset, so that all that we knew earlier is not necessarily entirely wrong, but can be thought of as a small subset somewhere with some small correction. Maybe it would fit into the bigger picture. So that's the approach that we are going to take. Then coming to I'll come to the preposition later. So the next thing is composite, and there in terms of the composite, we are looking at the ability to perceive unity even amidst or within the diversity. So the diversity we're talking about obviously is about the fiber and the matrix over there, and the interface and the various other additives that could be there. Most composites, especially non-aerospace applications, even have voids. So the voids are also part of that diversity, which basically means air pockets which happen because of certain manufacturing issues. So it's reduced to a large extent in aerospace composites because of the way the composites are manufactured through autoclaves. But still you would have a certain level of porosity. The porosity will be a much smaller fraction compared to composites which are applied, let's say, in the automobile or other non-aerospace industries typically. But still you would have a non-zero porosity. So that's again another component to the diversity. So how are you going to manage all of that diversity? So I refer to the concept of equivalent homogenization, whereby there is a way in which we can look at the whole thing in a unified fashion. And finally, in terms of the structure, we said that everybody sees the chaos in it. So a chaos, for example, you take the even natural structure like the wood of a tree, the way it is constructed, or a skeleton of a human being. To somebody who's not exposed to biology, it seems quite scary. It's not scary in the sense of it being a horror, but more in terms of the complication of the construction. If you look at right from the skull to the spinal cord, which is the backbone rather, and then the other parts of the various bones that go into making it, the femur, etc. All of these, the way they are joined, the joints that are there, the elbow, shoulder, hip, etc., the ankle, it seems a mind-boggling thing as far as the structure is concerned. And so that for an untrained eye, it appears as if it is some kind of a chaos. But for a medical student of anatomy, let us say, or even a student level, but as they progress into being a doctor or a specialist in certain aspects of the physiology or anatomy, you would see that they see a certain structure in it. They see a certain order in that structure. The purpose of that, why nature has evolved things that the way it has. So same way, like the skeletal structure for an untrained eye appears as chaos, but for a trained eye, it looks like order. If you look at the semi-monocoque construction of an aircraft wing, for example, you would see cutouts of that in some of the lectures in flight vehicle structures, whether it is the cutouts of the wing or the tail or the horizontal or vertical tail, the stabilizers or the fuselage, you would see there are so many stiffening structures apart from the skin, and the way the skin's thickness changes, and especially if it's made out of composites, how the number of layers change, how the ply drops are done, and then how these are joined to the stiffening structures, and how each one of these major components like wing are joined to the fuselage, the stabilizers, how they are joined to the fuselage. It's as mind-boggling perhaps as the skeleton of a human being. So for an untrained eye, a non-aerospace engineer, in particular a non-structures engineer, it'll look like chaos. But for us, we see the purpose of each one of those components, be it the spar or the stringer or the longeron or the transverse stiffeners like ribs or in the wing and the tails, or the bulkheads in the fuselage. They all have a particular purpose. There's a certain stress transfer or load transfer that takes place from the external environment, the way the load is applied, to eventually wherever it needs to be transferred, and therefore make the aircraft fly and fly in one piece instead of breaking apart. So the load bearing capability is built in because of that, what others see as chaos, but we see as order. So in that ability to see the order within the chaos, because that chaos is not just any other kind of a chaos. There is a method to that madness. We say something is chaos when we don't understand the science behind it or the mathematics behind it. It remains in the realm of chaos. But once we understand what it is, we see the order in it. And we are the structural designers, have designed the semi-monocoque construction in a particular way to minimize the weight and still be able to bear the load, so to offer certain strength, stiffness and stability to the aircraft, and at the same time contain all that it needs to contain within it in terms of the passengers, the other payload, the various other components like the avionics, the fuel, the engines, the propulsion system, etc. So all of this has to be done in a particular with a particular logic to the design. So there is a method to the madness. What others see as madness or chaos, there is a method to that. And the best analogy that many of you probably understand is also in a computer, for example. However sophisticated the computational system might be, the operating system and the software and the hardware, you would see that a random number generator would really not be generating something random. There is a certain coding done in order to do the random number generation. So if you go into the actual details of that, you would see that there is a method to that madness as well. So for all practical purposes, it's a random number generator. The correlation between adjacent numbers which are generated might be something very difficult to discover just by using the data set. But for the person who has written the algorithm to generate that, he or she knows that there is a certain procedure, an algorithm, very complex nonetheless, but there is a certain pattern to it, and that pattern is what brings about the order in that system. And that's why we talk about, even in computational realm, we talk about structures, computational data structures. It's very funny that sometimes when we get students to the aerospace department for their interviews, especially if they are from an electronics, electrical or a computers background, and during the interview process we say that there are 4 panels, one for structures, one for propulsion, one for aerodynamics and controls. You go to the panel which suits you best. So then we see a lot of electronics and engineers, computer engineers and electrical engineers coming to the structures panel thinking that it's about data structures. So but essentially the language is for a particular purpose. So why we call that as data structure and this as a particular aircraft structure, in the superficially it might look too different, but what essentially is there is that there is a certain set which appears to the untrained eye as chaos, and what to the trained eye appears as an order. So that's the reason why there is a structure built to it, because that chaos itself was created by us. We, the structural designer, created that chaos, and therefore we are able to perceive what is the order in that chaos. When we say we, I mean as an entire profession. I may not have been the part of the design team, but when I look at an aircraft structure which is designed by somebody else, I can see some order into that chaos. Whereas the actual team members who designed it would see even more order into it. But the whole idea is that as structural engineers, whether as designers or as those who are just going to be analysts, it just means that we should be trained enough to be able to see, even in that complicated structure which we call as chaos, what is the order? I mean, in the sense that what is the purpose behind each one of those structural components, why they are used, and how they correlate with the other components, and essentially form a team. Just like a human team can achieve far more than what the individuals can, that semi-monocoque construction of stiffeners plus the skin achieves something which individually each one of those items cannot. Same thing with the previous term that we saw, the composite, where we are looking at what the fiber cannot achieve by itself, what the matrix cannot achieve by itself, the fiber plus matrix combination of the composite is able to achieve. So that is the whole idea of trying to look at the bigger picture, or see from where this whole thing happened. So essentially what is happening is that if you look at the last column, whether you're talking about the model, motion, diversity or chaos, I'm still yet to come to the preposition, but all of these are creations of us, the structural engineer. We as a structural engineer look at a particular structural component or the entire structure and create a model out of it. These days aircraft companies work with the structural models of the entire aircraft, a mind-boggling complication in terms of the number of degrees of freedom, the number of elements required for a finite element analysis. Even if it is a dimensionally reduced model for various components, it's extremely complicated. But nonetheless, there is a model which is developed, and who's developing that? It is we, the engineers, we, the structural engineers as a team, are developing that model out of the reality that is there. Even before an aircraft is made, the model is developed so that we understand various things that could happen under the typical loading environment from a computational simulation, and then take over those learnings into the actual design and therefore the manufacture of the aircraft. First the fabrication of the prototype and eventually the optimized structure which is manufactured. So we have to understand that every one of those items that we have in this last column are actually the creations of us as the structural engineers. So the motion of the aircraft is created by us, the engineers, the aerospace engineers, by having this propulsion system, and then you're having the wings which can generate the aerodynamics forces like the lift and the moments which are required in order to perform certain maneuvers, and therefore we are able to have this motion. So we are creating that motion into the system. We have created the model to understand and improve the system, whether it's a non-existing system for the design, or if it's an already existing system which has undergone, let's say, some failure or something. It's an old system which doesn't have a sophisticated model which can help analyze why the failure happened of a particular structural component or the accident of the entire aircraft. Then we try to develop a model for that case as well. So whether it is the model or the motion, we are responsible for it. So we should understand that we have that ability to respond, which is what responsibility is all about. So we are responsible for creating that each of those items in that last column, either directly as when we say we the individual members, if we were part of this analysis or design teams which created the models, the modeling team there, or in terms of eventually looking at a model which has already been created by the rest of our fraternity, that is the other structural engineers whom we may or may not know. But once they have created, because we speak the same language of the physics and the mathematics, so we are able to understand what is the purpose of the various features of that model, why the particular discretization was chosen for the finite element analysis, what types of elements were chosen there, how the nodal connectivity was done, how the stiffnesses of the various elements were evaluated, and how those stiffnesses were basically assembled, and then how the overall governing equations were developed in terms of a computational model, and how eventually it was the rigid body degrees of freedom were removed from it, and then the entire system was solved for a particular purpose. So how they or we approach that, we should be aware of. So in that sense, we have created the model, we create the motion by appropriately designing the aerodynamics and the propulsion systems in particular, and therefore the structural engineer needs to cater to that those aerodynamic requirements, because the aerodynamicist only decides what is the airfoil shape. Who gives that shape to that airfoil? We, the structural engineers, by putting the material in a particular direction and assembling it in a particular way. So eventually whatever their wishes are, we are trying to fulfill as a structural team, and therefore the model is created by us, the motion is created by us, the diversity in terms of putting the fibers and the matrix in a composite or in a hybrid composite. You have glass fiber epoxy somewhere, you have carbon fiber epoxy somewhere else. And metals are not completely done away with. Most aircraft have 50% or more by weight of metallic structural components still. So where we put those metals, what types of metals we have, the steel alloys, for the landing gear, the titanium alloys for some of the engine components, the aluminum alloys where they are required in certain places where they might be functioning better than composites. And as we go into the future, we have to look at the probable use of metal matrix composites, ceramic matrix composites, carbon-carbon composites, etc., that we briefly touched upon in the previous class as well. So all of this diversity is created by us as well. So this diversity is also created by us. And eventually that chaos, what looks like a chaotic structure, is also created by us. But once we see the purpose of each one of those elements, we see the order in it. So that is essentially what we are going to look at over here. So are you able to see my blackboard now?
Yes, sir.
Okay.
Yes, sir.
Thanks. So let's start with each one of these. So let's start with the first term, nonlinear. And we said that we are trying to perceive reality even amidst the model, right? So essentially what is happening here is that this is possible, as I said, only if there are certain characteristics that the model obeys. And what are those characteristics that the model is supposed to accomplish? One is the reliability of the model. So in other words, we have a model which is reliable in the sense that it's as closely depicting the reality as possible for the given purpose. See, and the purpose could be preliminary design, in which the model need not be as sophisticated. It could be a reasonably simplified model, or it could be a detailed design, or it could be, even more importantly, in an accident failure investigation, where you need to go to more and more sophisticated models. So what is the reliability aspect there is in terms of meeting certain requirements like let's say accuracy. So whereby we mean that the error between the reality and the model is as small as possible. And for this, we need to choose the parameters of importance to us. For example, it could be the probability of something, some particular structural component, a primary structural component, like a rotor blade failing. So what is that accuracy that we can get in terms of that quantity? Or let's say the stress at a particular point, or a displacement at a particular point, a strain at a particular point. How do we try to obtain those as accurately as possible? So that is one aspect to it. So obviously we want to have the accuracy as high as possible. But as you keep going to models which are more and more sophisticated, which can give you that accuracy, it's obvious that the efficiency is going to go for a toss. So in other words, these are counter requirements. When one goes up, the other goes down, but essentially you want both of these to be high enough. So is there a balance that we can make between this accuracy and efficiency? So only when, for a desired level of accuracy, you have as efficient a model as possible, you have a reliable model. Otherwise, you might have a very accurate model, but it takes days to run. It's not going to be of much use, especially if it's like let's say detailed design or something. You take so much time to do the design. Eventually, when it goes to the market, your competitor has already introduced a very similar aircraft into the market, which is already doing very well. So you have lost the entire business over there. So the time to take it to the market is very important, and to reduce the time and therefore the cost involved as well, which means that the efficiency plays as important a role as the accuracy. And it's not just in taking products to the market. Even if it's a structural health monitoring system, for example, it's a real-time system that you would have, and even though the computational systems on board of an aircraft or a helicopter or any flying vehicle are improving day by day in terms of what they were a few decades back to today, still they are not as good as the supercomputers that we have on land, because we can't afford that kind of weight penalties to take such massive supercomputers. Those supercomputers also, in terms of their weight footprints are reducing, but still from an aerospace perspective it's very high, and we can't afford to do that, which means that with the kind of hardware and software capabilities that we have on board, can we do real-time analysis and get real-time information for the pilot in terms of the health of a particular structure. In the case of a aircraft, it could be, let's say, the vertical tail or the rudder of that vertical tail, which is essential for the aircraft to do the yawing motion. Is that healthy enough, or is it going to fail soon? Can the pilot get an information about that, so that he or she can make amends in terms of the flight path? The original plan can be changed, and the nearest airport can be used to land safely to avoid a disaster. So when something like that needs to be computed based on the sensors that are there in the various structural components, and the information has to be taken to the pilot over there, then you need something which is not only accurate, because if it's not accurate, it can give a false alarm when the actual rudder is not going to fail, but the pilot might get a false signal that it's going to fail, and he or she might land the aircraft, causing huge delays for the passengers unnecessarily. Or it could be the other way around, the other extreme, where the rudder is actually going to fail, and if the model that you have developed is not accurate enough for the structural health monitoring system, the pilot might get an information that it is healthy and continue the entire flight, intercontinental flight, and midway there is a disaster and the aircraft crashes, and it could be fatal for the crew as well as the passengers. So accuracy is so very important, but at the same time, if that information, whether the radar is safe or not, rudder is safe or not, or for that matter the elevator or the aileron or the wing or the certain other components, even the engine components these days need to have integrated vehicle health monitoring systems, what are known as IVHM. So when you develop all these, the pilot is supposed to get real-time information on the health of these. So the calculations based on your model has to be done, not only that it should avoid false alarms, and or you should not have situations where you have a failure which is going to happen and it's not revealed to the pilot. There the accuracy is important, but it also has to do all of these quickly, so that that real-time aspect is there. Because if the information comes to the pilot, let's say 10 minutes late, that the rudder is having a serious problem, it might be too late for the pilot to effect landing in that kind of a situation. Or if one of the engines has failed, as you see in this particular aircraft, one of the engines is missing over here, the other engine is there. So let's say the attachment of the engine to the wing was weak and the engine fell off. So you have just a single engine, and that's why you have in passenger aircraft multiple engines to bring in that redundancy, and therefore have the capability to fly. But in this kind of a situation, what is going to happen is that though this engine will have a certain thrust, and therefore it can still have a forward velocity, and because of the forward velocity the wing can still generate a non-zero lift, and therefore it's not going to crash, just have a free fall. But at the same time, this engine is going to cause a moment because of the thrust line being away from the CG, which is on the center plane, which is the plane of symmetry for this aircraft. It's going to yaw, and if it is going to yaw, you have to deflect the rudder in such a way that this vertical tail is creating a moment in the opposite direction, so that it is still maintained. And once the rudder is deflected, the drag is going to be more, and therefore the thrust required for achieving the same forward flight at a given altitude at a given speed is going to be much more fuel burn. So you're going to quickly be burning out your fuel, etc. So there's so many complications that are there in the in designing the integrated vehicle health monitoring system, which means that for an accurate model, the computational algorithm is going to be taking a lot of time. So how do you still bring it to the minimum possible level by optimizing the mathematics of the model, optimizing the science of the model in such a way that it can still give you in a reasonable amount of time that the pilot has to basically land the aircraft. Even more important in the case of a helicopter, where you have this auto rotation feature, where even if the engine fails, because the main rotor is still rotating, that momentum of the main rotor can be utilized in order to effect a safe landing. That's why helicopters are a little more safer in engine failure compared to fixed wing aircraft. But of course, there are other situations that they fly in much more stringent environments, closer to the ground, in environments which are urban or forest kind of areas, where there could be things which can come in the way of the rotating parts, which are the main rotor or the tail rotor. So there are other issues associated with that. But in a proper flying environment, if there is an engine failure, you have much more time to land a helicopter than you would to land a fixed wing aircraft. But even there, that amount of time for the pilot to get an information, yes, there is an engine failure, and therefore I have to effect the procedure for auto rotation, whereby I disengage the main rotor from the engine, so that otherwise the main rotors will fast lose its momentum because it is driving in turn the engine. So it's like in a motorbike or a car, you would have observed you use the clutch basically to disengage the engine from the wheels, and so therefore you have much more momentum to utilize in order to take you forward when there is an emergency situation. So the same kind of a situation you have over here through the auto rotation feature, how you go about doing that. So in all these situations, you see that the efficiency is so very important, almost as important as the accuracy. Only when both of them are there, you have a reliability. Then in terms of the reliability, again, there are two more requirements which are again contradictory to each other. One is the rigor of that model. So you want to have a very rigorous model, in the sense that the science behind the materials, the science behind the geometry of that structure and the load transfers, etc., should be understood well. In particular, the physics is what we are talking about. So that rigor has to be there, and especially we who are in academic kind of situations, if you want to publish papers and other things which are going to be peer reviewed, your manuscripts which you submit, unless and until there is a certain rigor to the science or the physics in it, it will not be accepted. So they'll find holes in your manuscript or in the logic that you use to develop your equations and solve them. So that rigor is very important. But once you have too much of rigor, what happens is that when you build a software out of it, the engineers who are going to use it in a routine basis are going to find it very difficult to use that. So in other words, there is no engineer friendliness. So that's where the graphical user interface comes in. For any software that you develop, you need to have GUI, so that those engineers who are going to use it on a routine basis do not have a need to understand the physics behind it, the complicated equations that are used to solve the problem, etc. But using the GUI, they have an easy way to accomplish this whole thing. So that's where the engineer friendliness comes into picture. So this is the contradictory requirement contradicting the rigor. So you have to strike a balance between these two. But as I said, the GUI can, if properly designed, can take care of this. So there is a solution to all of these, but it's important to understand the issues so that you resolve them a priori, even before the issue is caused. So that is the whole idea of understanding this. So that's all that's about the reliability in terms of all these requirements. So once you have all of these, then your model is reliable, and therefore it predicts as close to reality as possible. But even when it predicts, it's just giving you a data set, or maybe if the post-processing is good enough, it gives you in a graphical output what is basically observed. But you as an engineer, a structural engineer in particular, is expected to decipher that output, because if the input has been even one of the inputs has gone wrong, the output can be meaningless. It could be just garbage in, garbage out. So in other words, you have to first of all check whether the model is appropriate or not, the validation. And then if it is a validated model, then are you able to do the inference from that model? So in other words, the model is giving appropriate results from the post-processing. Then you are going back from the you created the model from the reality, but now you are going back from the running the model and getting its output to the reality. That's where what you do as a structural engineer is very important, the process of inference. So you have to infer from the data that it generates or the graphical outputs that the software generates, what is the takeaway for the reality, what corrections to the design need to be made, what improvements need to be made from an optimization perspective, etc. So depending upon the kind of problem, the kind of inferences are different as well. So this particular inference therefore becomes the most important task of engineers today. In earlier days, there used to be a lot of this the calculations which models do automatically on a computational system today. That was the donkey work that we as structural engineers had to do. Even as structural engineering students in BTech or MTech PhD, we had to learn a lot of things which today is done routinely by computers. You don't need to actually do that. So you need to understand your role as you go out and not try to learn those same old things. Maybe for your own knowledge and understanding you can do, but from a perspective of being more useful and for the entire system, the aerospace ecosystem, to utilize you in an appropriate way, you should be good at certain things which are essential in your day-to-day tasks as a structural engineer. And that's where the inference becomes the most important task, because the drudgery or the routineness of the mechanical tasks have been taken over by computers. So that is an ability that you need to develop. And so if you look at this whole thing, we also said that this whole in terms of what is happening here, from going from the reality to the model and back, you are creating the model, and from the model's output you're getting the reality. Though you're typically doing it for a nonlinear model, the linear can be considered as a special case of this whole thing, so that the linear model is a special case of the nonlinear model. And similarly, if you look at this whole process of creating a model from reality and doing the inference, it requires a lot of devoted effort from the engineer. So see, anything can be successful only when you have devotion to the task. If you're devoted to a particular task that you're doing, whether it's an assignment or whether it's an exam or whether it's in your job, if you're devoted to that task, then automatically the quality of the task improves and the output is better, and the results are up to the required mark, or either your anticipation or the anticipation of your instructors and or your team leaders. So this whole process of going from reality to the model and coming back from the model to reality, or the ability to perceive that reality even amidst or within the model, is essentially a path of devotion. So this is essentially So unless you are devoted to this whole task of developing the nonlinear model, and you're able to understand that the model is nothing but a replication of that reality, and therefore whatever the model outputs, if it is validated well enough, then you should be able to infer certain takeaways, useful takeaways from it. All of this is basically the path of devotion, what in our scriptures we call as the bhakti yoga. So this whole concept has unfortunately been hijacked by the religious people to say it's part of the religion. But even if you are an atheist, the whole idea is, if you want a particular task to be successful, you need that devotion towards that task. Whatever task you're accomplishing, you need to be devoted to that task in order for it to be successful. And that devotion is all that we are calling as bhakti yoga, which is basically the path of devotion. So that is essentially what we have over here. Let's go to the next one. Okay, so the next thing that we were talking about is the mechanics. Okay, so in mechanics, we said that it is the ability to perceive the stationary principle. So let me in the motion, or even amidst the motion. So you are able to look at certain stillness. See, what is stationary? Stationary means something which has come to a rest, something which has come to a standstill, right? So essentially what we are talking about is a maxima or a minima over here. And you're already familiar with the total minimum potential energy principle, etc. So those are all examples of that, and there are various other examples as well. What we are going to primarily look at in this course, which is the variational asymptotic method, then those which are ascribed to various people. So this is of course by Berdichevsky, whom I will talk about a little more detail later on. And then something that we will use very effectively in the overall structure is also the Hamiltonian, which was a gift to us by a scientist by name Mr. Hamilton. And then we have Euler and also Lagrange. You're familiar with the Lagrangian approach. So, and the combination of Euler and Lagrange for what is known as the Euler-Lagrange equation, because this whole process of going from the motion to the stationary principle is accomplished by a branch of mathematics, what we call as the calculus of variation. So all of us have studied calculus as part of school, mathematics, high school mathematics, but calculus of variations is basically a generalization or extension of that many of you might be familiar with, which is dealing with not functions but functionals, which in the most simplified manner can be thought of as functions of functions. So you're basically having a certain dependent variables, which in turn are functions of independent variables, and those dependent variables are unknown quantities. You want to find those how those dependent variables depend on the independent variables, so that they maximize or minimize a particular quantity, which could be a Lagrangian, which could be a Hamiltonian, or some other notion of functional, which can be derived through the energies associated with the system. So that is essentially what we are doing in this. So the whole idea is that when you're doing a maxima or a minima, in either case we know that from even basic calculus, if you want to find the maxima or the minima of a function, what we do is we set the first derivative of that to 0. So then we go look at the second derivative to see whether it is positive or negative, and then decide whether it is a maxima or a minima. So on the other hand, in the case of an objective function which involves functionals, it could be a little more complicated, especially when you have constraints and you're adding those constraints, some of which could be constraints in the form of equalities or inequalities. Some might be integral constraints or non-integral constraints, point-based constraints, which could be certain restrictions which are imposed on the overall behavior and the motion of the system. So all of that has to be accomplished within this whole picture. So you might not know whether it's a maxima or minima until you go to one more step. And very fortunately, the solution actually does not require us to go to that additional step, because most of these governing principles are just stationary principles. As long as you find out that the the particular function is stationary at a particular location. So if you call that functional as, let's say, some I, which is in turn a function of certain unknown quantities, like let's say wi, which in turn are functions of some xj, where xj are the independent variables. So these are the independent variables that you have, and you have a set of dependent variables which depend on the independent variables, and these are unknown quantities. And this whole functional is defined over a certain range of the independent variables, xj varying between certain range of things. For example, if you're treating this as a beam and x1 is along the length, x1 can vary from 0 to L, x2 can vary from, let's say, minus d by 2 to plus d by 2 if you're treating this as a circle of diameter d, this cross section, and x3 is also varying from minus d by 2 to plus d by 2, where d is the diameter of this cross section. So that basically is the range over which this entire thing is defined. And this I, the way this overall bracket is, could be an algebraic function, it could be a differential operator, but more often than not it is an integral operator. And within that integral operator, it can contain differentiations, it can contain algebraic expressions, and those algebraic expressions in turn can be polynomials of higher order. It could be involving trigonometric functions, hyperbolic functions, etc. Whatever, there could be various complications that are involved over there, and you're trying to basically minimize that, which means that what we do is set the first variation of that, which we represent by the mathematical notation delta of I, equal to 0, and therefore we arrive at a certain set of equations, what are known as the Euler-Lagrange governing differential equations, GDE in short. So the Euler-Lagrange governing differential equations arise when you set delta I equal to 0. But as a byproduct, you also get, apart from the governing differential equations, you get boundary conditions in a regular problem, even statics problem. But in a dynamics problem, in addition to the boundary conditions, we also get certain initial conditions that are associated. And in turn, the boundary conditions could be either in terms of the generalized forces, which could also include moments, both distributed as well as concentrated, and then you could also have it in terms of displacement, again generalized in the sense that it could involve rotations, again over a continuous range, or it could be at a point, at certain points within the structure, the boundaries of the structure. There could be internal boundaries, external boundaries, etc. But at all of these boundaries, you will get these boundary conditions and initial conditions also as a byproduct of this overall process of calculus of variations that you're applying. So this is another prerequisite for this course. So those of you who are not familiar with the calculus of variations, I would urge you to look through some calculus of variation. By the time we reach that level in this course where we are going to apply the calculus of variation to various problems, you have sufficient number of weeks to get to speed on the calculus of variations. I'm sure some of you are already aware of the calculus of variations, but those of you who are not exposed to this concept of the very first variation, the Euler-Lagrange equations, etc., in constrained problems, where the constraints can be in the form of algebraic constraints, or it can be in the form of integral constraints. It could be also either as equalities or inequalities, less than or greater than a particular quantity, and how you incorporate them using Lagrange multipliers into the objective function. All of these are things that you need to be familiar with, because the variational asymptotic method, when we apply, it's going to assume your knowledge of the calculus of variation, so that you see how we go from the original model, which is expressed in terms of the kinematics, in terms of the material behavior through the constitutive law, how we are going to take that forward in terms of understanding the kinetic energy, the potential energy, and therefore either the Lagrangian or the Hamiltonian Hamiltonian, and then how we are going to use the leading order terms there in the variational asymptotic method to arrive at an approximate set of governing differential equation, approximate set of boundary conditions, approximate set of initial conditions, which are nonetheless asymptotically correct. So the whole idea of that is encompassed in this mathematical process of calculus of variations, which is one of the main building blocks of any variational principle, not only variational asymptotic method. Even if you were to use the Hamiltonian or the Lagrangian in an appropriate way, you do need to understand the calculus of variation. So it's a very useful mathematical tool, not only from this purpose, but from many other applications, not only in structures, but in various other branches of aerospace engineering and various other branches of engineering as well. So it's essential for you to revise through that calculus of variations approach. So then essentially what we are doing is that we are going towards a maxima or a minima, which is what the stationary principle does. And that's essentially what we are talking about as a stationary principle, is some kind of a stillness. So we are accomplishing a certain stillness. What is that stillness? The stillness in I. Because we are taking the first variation of I and setting it to 0, that means it reaches either a maxima or a minima, basically a stationary value. In other words, it has reached a certain stillness, okay? Which is what in our scriptures we call as the Mahasamadhi. So in accomplishing that, we call this whole process, see, basically what we are doing is we are converting the motion to that. And the motion is basically nothing but a vigorous dance of life. So you have a vigorous dance of life, full of activity, and you're reducing that to a stillness, which is basically your Mahasamadhi. So this is essentially this stillness is in the midst of absolute activity, dynamic life, is going to happen only when you have a path of discipline. So just like the previous one in nonlinear, when we moved from reality to the model and back, we talked about the path of devotion. So here we are talking about the path of discipline. Okay, so this path of discipline is what we refer to as either the Hatha Yoga or Raja Yoga. So that's essentially what it is. Again, many people see this with a religious connotation, but there's nothing to do with religion over here. Discipline is required in order to have any major accomplishment. Just like devotion is required, you have to be devoted to any tasks that you do in life in order for it to be successful. You need to follow certain discipline in order to be able to put that devotion into action. So without that, the just saying that I am devoted to my task doesn't help. You have to have a certain discipline in terms of reaching that particular stage, and that is basically what the Hatha Yoga or the Raja Yoga does. And this whole concept of the Mahasamadhi or stillness is basically what we are also used to in Patanjali Yoga Sutras, where we say even the concept of asana, which unfortunately has become just a twisting of the body these days, is to accomplish that stillness in the body, stillness in the mind, stillness in the intellect, so that you are able to look at a bigger picture, the bigger perspective of life. And that's why you define asana actually as whatever is stiram and sukham, that is asana. That is, stiram is basically stability. And in a structure also, we look for the elastic stability, the aeroelastic stability. It should not get into flutter, it should not get into aeroelastic divergence, or it should not get into buckling, which are all instability, ways of failing in instability, where the material is still not broken. In other words, the material is still well within the ultimate tensile strength or whatever its failure strength might be, but still a failure has happened from a geometric feature, and that's because you have not attained a certain level of stability, what we call as sthiram. And sthiram sukham iti asanam, we say. So that which is not only stable but is also comfortable. So in other words, what is sukham? The sukham or the comfort that you're having is in terms of an aircraft structure, the load transfer. The load has to be transferred from the, let's say, the skin on which the aerodynamic load is acting. It has to immediately transfer it to the other structural components that are there through the stringers, first from the skin to the stringers, and from the stringers to the ribs that are there, and from the ribs to the spars that are there, and from the spar to the fuselage. So then you think of this as a cantilever beam. It has quickly transferred all of the loads. Otherwise, if it had not, the pressure that the aerodynamic flow of air over the wing is going to have on the skin, which is so thin that it is going to fail right away. The fact that you have all of the stiffening structures and it transfers the load means that it is having a certain level of sukham or comfort. So you have to have a certain level of stability, and even if you give away some of that stability, because the skin can actually undergo buckling and it can operate in the post-buckling regime, which means it has given up some of its sthiram, but it still has that sukham in the sense that there are adjoining structural components, namely the stringers, the spars, and the transverse ribs, which can take all of that load and therefore free the skin from that its task of doing that. So it's designed in such a way that it can get into the post-buckling regime, so that you reduce the overall structural weight of the aircraft, and therefore the overall weight of the aircraft itself, and therefore enhance its performance in terms of having a longer range or the ability to carry more payload, or in terms of the speeds that it can achieve, or if it's a fighter aircraft or something, in terms of the maneuverability that it needs to have. All of this can be built in once the structural weight comes down, and that proper design requires building in a certain level of sthiram and sukham, or stability and comfort, in terms of the stress-free state or reduction in stress, or various ways in which you would see, and I would refer to it as we go through in the rest of the course, when we are doing some kind of a stress relief for certain materials through their very behavior, and also when we talk of creep and things like that, we will come back to this. And also that's as far as the material is concerned, and from the structural design itself, from the geometry design, like what I just described about the post-buckling operation of the skin, where the stress transfer is done. If the stress transfer had not been done, the stress levels in the skin would have been so large that the skin would have ruptured, and a huge failure of the wing, and therefore of the aircraft, and therefore a fatal crash of the entire aircraft could have happened. So there's so much of repercussion to this whole process if we don't understand this what simple thing it is there. And it's if you understand it from this bigger perspective, you can relate to it so well that you don't need to memorize these things, or approach it in a way that it's a difficult task, this course or its exams or its assignments, or eventually its application in your careers. It can all be just a game, what is called as a leela, instead of it being a certain rigid task that you have to do, imposed upon you. So instead of thinking of it as an imposition, if you make the rules of the game as your own rules, then essentially you become a part of the game, and therefore it's much easily accomplished. And just as in the first case we said linear is a special case of nonlinear, here we will treat statics as a special case of dynamics. So this is essentially what this thing is all about. So that is as far as the second entity or mechanics that we dealt with. So next we'll take up the composite, which is what we said, that we have to perceive, or we should have an ability to perceive unity in diversity. And as I already mentioned, this whole process by which you have created the diversity because of the design. You chose the fibers, you chose the matrix. So everything in that last column that you have, this particular column that you have, is something that is created by you. Now you're trying to go back from that to the reality. So that is unity. So that's essentially what we call as the equivalent homogenization, which is essentially coming up with an imaginary material which has an overall behavior which is similar to what this combination or a mixture of the fibers and the matrix does. And so that is means that you are getting the overall properties of the composite. Some function of the composite is going to be, let's say, some property P of the composite is going to be a function of that same property of the fiber, the same property of the matrix, maybe a few other properties influence it as well, and then the volume fractions of the fiber and the volume fraction of the matrix, and maybe you have certain other additives as well in the whole structure. So you're basically taking into account all of that. So how do we achieve that is what equivalent homogenization is all about, where we move on from the diversity back to the unity. So so essentially what we are doing in this whole thing is that in the equivalent homogenization, you can think of it as let's say analogy you could have is as a salad bowl. So if you see a salad bowl, whether it's a fruit salad or a vegetable salad, you see that the individual quantities are retaining their nature. So if you could have, let's say, beetroot and cucumber and carrot, etc. in your vegetable salad, tomatoes, etc., they still retain their individual identities. You can look at your salad bowl and you can identify each one of those components. So that's essentially what a composite is, as opposed to an alloy, where with your naked eye you're not able to distinguish within that aluminium alloy where the various other additive metals are there. Whereas in a fiber matrix kind of a situation, even though the diameters of the fibers are of the order of 10 microns or so, you are actually using toes, and you can actually in just by visual inspection you can see where the fibers are, where the matrix is. So that distinction is there. So that is the salad bowl, as opposed to let's say a smoothie or a juice blend that you have, where it has lost the whole thing. So this is more like an alloy, whereas this is more like your composite, right? So that's basically you're having a balance between these two. You know that there is a diversity, but for the purposes of modeling, you're going back to that unity to make things simpler in an overall behavior of the entire composite structure, what kind of deformations it's going to have, what kind of equivalent homogenized stresses it's going to have, equivalent homogenized strains it is going to have. So in other words, if you look at within a composite structure, there could be fibers which are running, and therefore the stress within the fiber and the stress in the matrix is going to be different. But in the equivalent homogenized structure, you're taking a certain infinitesimal volume which encompasses the fiber and the matrix, and you are basically integrating in such a way that you integrate all these stresses in a given direction of a given kind, be it normal or shear, and then you are dividing by that volume after the volume integration. So in other words, you're averaging out the stresses over there, and the averaged out stress component in a particular direction is going to be correlated with the averaged out strain in that particular volume, and eventually you're going to reduce that volume not to zero in the limit as it goes to zero, because then you would end up with either the fiber or the matrix, but the minimum volume that is required there, what we call as a representative volume element, which is in turn made out of a certain set of unit cells. So that's essentially what we are going to do as an approach over there in that equivalent homogenization, whether it's for the material properties or for the stress and the strain. But eventually, when we want to look at the actual phenomenology of the failure, then we have to understand whether the structure has failed because of a fiber breakage, in which case we need the stresses within the fiber, or we need to understand if it's a matrix cracking, what are the stresses within the matrix, and that's where we have to go back from the unity to the diversity, at least in those regions where the failure is happening. We can't do that everywhere because it's computationally too intensive to do that, to treat the entire structure of a wing, let us say, as both fibers and matrix. You would run on for years, even in the supercomputers, and never achieve any useful solutions. So you have to do this equivalent homogenization. You find out the spots which are going to be of critical nature. Usually it could be because this is a cantilever kind of boundary condition, and the kind of loads that happen on the wing because of the lift distribution in general, most importantly, but also the other aspects like the aircraft engine weight and the drag distribution, the moments that are coming from the control surfaces, from the aerodynamic flow, from the concentrated loads that are there because of the various pods that are hanging, or the fuel that is contained within the wing. Because of all of these reasons, usually it is the root which is the of the cantilever where the stresses are very large, and within the root, again, because the bending stresses are maximum, the farther away from the neutral axis it is, the more the stresses are going to be. So therefore the close to the root where the wing is attached to the fuselage, and on the wing the top surface as far as the compressive stresses are concerned, and the bottom surface as far as the tensile stresses are concerned, are going to be critical. So those regions, is a fiber breakage going to happen, is a matrix crack going to happen. So then you might have done the equivalent homogenized model for the entire wing, the various materials that are used, including the composites, and then once you have done that, if let's say the root is made out of a composite, then you have to come back in those root regions, especially on the top skin and the bottom skin, or even the for the spar, if it's made out of an eye section, the flanges of that, you come and explore that in certain regions where the stresses are large, the stress concentrations are there, etc., because of the joint as well, apart from the fact that it's a cantilever kind of geometry. Now those regions, we go back from the imaginary equivalent homogenized material to the actual distribution of the material within that, which is nothing but your fiber and matrix and maybe the other additives and voids, etc. So then you try to get the stress values within the fiber, stress values within the matrix, and then explore what is actually going to happen, what kind of phenomenological failure is going to happen. Or an accident has already happened, you have a particular section there, or it could be just a lab level experiment, or in an aircraft you're just doing a wing level experiment within the aircraft lab, and then you basically subject it to certain loads until it fails, which might be certain requirements from the certifying agencies like FAA or DGCA, CEMILAC, etc. So then you analyze those regions to see what kind of damage can actually be happening, whether it's fiber breakage, fiber matrix debonding, the matrix cracking, or delaminations, or combinations of these, which is the initiation and which is leading to what, and how is that process eventually leading to the overall structural failure. So this whole process to understand, you have to go back. So from the unity back to the diversity, and that's what we call as the concurrent multi-scale modeling, where we are able to go back at least in regions of interest, regions where stresses are very large and or displacements or strains are very large. You try to go to that region to understand more in terms of the actual materials, what is happening, and probably that can help you improve the design to either delay the failure or completely avoid it. So these are the things that essentially you're doing in this whole thing. So what is this essentially accomplishing, this whole task? Of going from unity to diversity and back from diversity to unity, and once again back from unity to diversity to do a detailed investigation. So all of these are essentially the path of knowledge. So just like we had the path of we had the path of devotion in the case of the nonlinear, and in the case of the mechanics we had the path of discipline. So just as much as devotion and discipline are important, you need to have knowledge. So without knowledge, just having discipline and devotion doesn't take you anywhere. You're just going to do only lip service. There's not going to be any accomplishment. So this is where the path of knowledge, or taken to a higher level, the path of wisdom basically comes into picture, and what even more beautifully is said in our scriptures as the Jnana Yoga. So which is essentially, jnana means knowledge, and yoga is the path towards unity, and therefore jnana yoga is essentially taking you from the diversity to the unity through that knowledge that you have. And if you make it a little more specialized, we call it as Vijnana Yoga, or Vi, or Vi is the prefix, which just means special. Pra or Vi is used to say something is special. So a special knowledge is nothing but your wisdom. So that's the distinction between knowledge and wisdom. Or Vijnan is also used for science. So science is basically a specialized kind of the knowledge system where you're trying to understand the cause-effect behavior and trying to utilize that, which is what engineering or technology is all about. So that's essentially the path of knowledge or wisdom, because what you're trying to do is go from diversity to unity, which is nothing but the essence of oneness. Unity is what? It's essentially the essence of oneness. And essence of oneness in what? It's the essence of oneness in purpose. See, the fiber and the matrix, if they are fighting with each other and doing things which are counterproductive, your overall composite is going to be taking a toss. The purpose of its design is not going to be achieved. So you should have an essentially that oneness in purpose. So we are talking of unity. It's not only in terms of the equivalent homogenization for a modeling purpose, but also the oneness in purpose of the fiber and the matrix, and the oneness in reality, which is the ultimate nature of things, that everything is one. And so that's essentially what this whole process of either equivalent homogenization going from diversity to unity, or the coming back in terms of a concurrent multi-scale modeling from the larger length scale to the lower length scale of the fiber matrix level, essentially is doing is to take advantage of that oneness, and at the same time exploring whether that oneness in purpose is achieved or not, which is not achieved when failure has happened. Obviously something has gone wrong, so you come back and understand the design from the basic component level, which is the fiber and the matrix. Or in an overall wing sense, you might have done an overall beam analysis for the wing as a cantilever, or for the fuselage as a simply supported beam, where the two hinges at which it is supported is the wing and the horizontal stabilizer. So these two are supports in which there is a simply supported beam with an overhang. So you see some portion of the fuselage is ahead of the wing in most designs. So there you basically have an overhang of a simply supported beam. So whether you're dealing with this as a simply supported beam or this as a cantilever, this as a cantilever, this as a cantilever, that is in a sense you're gone and looked at this whole structure in a unified way. But then this structure is actually made out of various components inside as spars, stringers, skin, etc. Coming back and doing that is what you come back to the diversity. So this back and forth motion is possible only when you as a leader, as an accomplished structural engineer, is able to see that unity in diversity, and at the same time is able to easily translate between the two. There's sometimes the model of diversity is important, sometimes the model of unity is important. Model of unity helps you to increase the efficiency of the model, whereas the model of diversity is going to help you increase the accuracy and look at each individual component, what's happening, why failure is happening, how we can delay that. So this ability to move back and forth between this last column and the second last column of this entire slide that we have been discussing is the essence of what the structural engineer is supposed to accomplish. So then let's go to the last one, which is basically the structure. Okay, so structure, we essentially, if you remember, said that it's the ability to perceive order even amidst or within chaos. I gave the example of the skeleton, I gave the example of the actual structure of wood in a tree, and then the semi-monocoque construction where you have various structural components, or in the case of the composite, even you're talking of the fiber and the matrix. But that we already talked about in the adjective to structures that we had just in the previous discussion, where we talked about the composite as seeing unity in diversity. Now you're taking that unity in diversity to one level higher, and that's where the overall structural behavior is, which I also discussed to some extent while discussing the previous concept of unity in diversity. So essentially what you're doing over here is nothing but the in going from order to chaos, or going back from chaos to order in terms of seeing what is actually happening, is essentially your path of action. So this is basically what the structural engineer is actually doing over here, is the path of action, what in our scriptures is essentially related to as karma yoga. Again, a lot of people confuse this with religious aspects, but it's nothing but the law of cause and effect. So anything that happens should have a cause. Whether you understand how to go to the cause or not depends on how developed your scientific knowledge is. So, and science is a continuously developing process. So newer and newer discoveries. Before Einstein, the way we understood classical mechanics, and once Einstein's theory of relativity, both special and general, came up, how we looked at the same mechanics at higher speeds, and how Heisenberg and others who Bohr, etc., who brought in the principle of uncertainty, and then how we understood the quantum mechanics, then the quantum field effects, where both the speeds are large as well as the sizes are very small. What is going to happen there? Very complicated things, which are leading to very useful things in terms of technology like quantum computing, etc. So all of this is possible only when we allow the possibility of our scientific knowledge to change. And at a given level, for example, today we do not understand the principle of gravitation quite well. So a lot of things that happens, though we have the Newton's law of universal gravitation, etc., we'll understand it at a bigger perspective. But why that force is generated in the first place, we don't have as good an understanding as we have of electromagnetism, for example, the electric and magnetic forces. So gravitational forces and also the nuclear forces between the protons and the electrons and the further subatomic particles that you have, the Higgs boson or the God particle as it is called, we have very little understanding because we have only visualized these through experiments or their behavior rather than actually witnessing these components either at very high speeds and or at very small length scales, much smaller than the fiber diameters that we are interested in from this particular course. So essentially, if you want to achieve that, you have to develop science more and more. At the same time, you are developing the application of whatever is the current knowledge of science in terms of engineering and technology. So that's essentially the path of action or karma yoga over here. And that action, essentially, if you want to convert that karma to what is known as a kriya, so you go beyond the law of cause and effect, your action has to be qualified by the fact that it has to be selfless. So in other words, the observer can influence this whole process of going from the cause to the effect and back. So how is that subjectivity in the observer or the seer basically being a part of this whole system? How can you remove that and make it more objective, or the bringing in that objectivity is what we refer to as a selfless thing. Of course, in social context, it becomes like a selfless service where you're catering more to the larger population than to your own needs and serving the needs of the others. So essentially, when we are bringing in this aspect into the logic that we are developing in science, that is the selflessness that we are talking about, where we are removing the observer from the subjective inferences that he or she gains by looking at an experiment and seeing how far we can go into the objectivity. And it's a big challenge even for those bodies of knowledge that are well established in physics like electromagnetism, etc. There is always an influence of the observer into this whole system, and it becomes a little difficult to deal with that. But from our perspective, what are we looking at in this structure in going from the chaos to the order in terms of designing that semi-monocoque construction of the wing or the fuselage to identify how many stringers you're supposed to have, what is going to be the cross section of each stringer. Is it going to be a T section? Is it going to be a hat section? What material is it going to be made out of? If it's going to be made out of a composite, how many number of layers or lamina we are going to have in the laminate, each one of those plies, what angles they are going to be, what sequence of those angles we are going to have in terms of the ordering of the laminate sequence, etc. Then within each one of those laminae, what is the volume fraction you're going to have for the fiber in the matrix. So this overall buildup of the structure is where we are bringing in certain order into the chaos. It looks for the untrained eye or to the non-structural engineer, it looks such a ugly, dirty system that the semi-monocoque construction is, just like for a non-biologist the skeleton looks. So but we have a certain purpose to this madness, as I said. Just like in the random number generation, there's a purpose to that randomness, that is the way it is generated. Here also, the way we design a semi-monocoque construction as structural engineers, there is a certain method to this particular madness. So I'll stop in a minute or so, where this whole process of going from chaos to order is what is done as a process of structural analysis or structural design, where we are going in the reverse direction, which essentially is to a large extent is done through computational models these days, so what we call as CAD, computer aided design. And then once you have analyzed and designed, that's not good enough. You have to build that, right? So you understand it from an order perspective in order for the modeling, but eventually the implementation has to be still in that chaotic construction, and that chaotic construction is what we do after analysis and design. We go to the build, and that building of the structure can take two forms, which is basically the initial prototypes, what we call as fab or fabrication, and then the manufacturing that we do. And again, to a large extent, that has been computationalized as well, what we call as the branch called CAM, or computer aided manufacturing. Again, within manufacturing, you can have two branches, the traditional methods, which were the subtractive kind of manufacturing, where you need to do after building the structure, you do certain machining, etc., to remove the material. Whereas today, slowly we are moving towards additive manufacturing. Already a few aerospace components, even with respect to the engine, are being made using additive manufacturing, loosely known as 3D printing, but involves more than that. So the additive manufacturing aspects are coming in more and more, and taking away certain parts, but still subtractive manufacturing, the traditional subtractive manufacturing remains the mainstay of most of the components, but slowly the percentage of components which are made through additive manufacturing are increasing as the additive manufacturing techniques are improving. The materials, raw materials which go into the additive manufacturing, their availability in terms of with better properties, and the way they come together through the additive manufacturing process are all improving. So there are many advantages in going from the subtractive manufacturing to the additive manufacturing. But whatever it is, essentially this overall understanding that it is the correlation between order and chaos as the cause and the effect, or one being what is being perceived by the untrained eye of a non-structural engineer, that is chaos, and what is perceived by the trained eye of a structural engineer as the order within that chaos, is what essentially we are trying to understand over here. So thank you. With this, we complete these four main components of the title, and I will try to put these two together, stitch these two together through that preposition of that is nonlinear mechanics of composite structures. Composite structures being the object, and the nonlinear mechanics being a certain aspect of it that we are studying. There are many other aspects to it, but this is a more important aspect that we are focusing on in this particular class. So how that existing object of composite structure, we are applying this process of nonlinear mechanics to the understanding of the science and the math, the science of the mechanics and the mathematics of the nonlinearity. How we are applying is that where the preposition of comes into picture. Once we do that, we would have got the overall bigger picture, and once we have the bigger picture in place, we will get into the nitty-gritties of the actual implementation of the nonlinear mechanics of composite structures. So thank you very much. So as is usual for every class, students are free to leave after this the end of the lecture, and those who have time and who have questions are most welcome to ask me, and I'd be happy to clarify to the extent that I can. Thank you. So anybody has any questions? Feel free to unmute and ask me if you do. Okay, thank you then. If you have no questions, we'll catch up again on Wednesday. It's a pleasure meeting you all. Bye-bye.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Bye-bye.
Thank you, sir.
Welcome.
Thank you, sir.
Welcome. Most welcome.
मृत्युञ्जय मन्त्राः त्र्यम्बकं यजामहे सुगन्धिं पुष्टिवर्धनम् उर्वारुकमिव बन्धनान् मृत्योर्मुक्षीयमामृतात् एते सहस्रमयुतं पाशा मृत्योर्मर्त्याय हन्तवे तान् यज्ञस्य मायया सर्वान् वयजामहे मृत्यवे स्वाहा मृत्यवे स्वाहा